Hi, my name's Michael, and I'm just going to chat for a little bit about my research. I'm currently a fifth-year PhD student at the University of Nebraska, Lincoln, and I'm advised by Alexander Sestroianu and Mark Walker. I have three projects that I've been working on lately. The first is about resolving monomial ideals and the implications that those resolutions have for the multigraded deviations. The second is about bigraded deviations and how those interact with the structure of the ring and rigidity properties of them. And the last is about quasi-complete intersection homomorphisms, with the idea of trying to figure out something about Quillen's conjecture on cotangent cohomology. So first off, multigraded deviations. The idea with this one is that if you take a polynomial ring and you quotient by some monomial ideal to get a ring R, and you go down to the residue field associated with such a factorization, you can fill in here the minimal resolution of K over R, which is has a DG algebra structure, and you can also fill in over here the minimal model of R, which also has a DG algebra structure, and the sizes of the sets Y and X are equal. And if you just take some other DG algebra resolution, maybe the minimal resolution for R over Q has a DG algebra structure, sometimes you can relate these two things. With either a surjective map going up or maybe an injective map going down, you can say something about the deviations of the ring, which is like a property of this resolution of K over R. You can say something about that just by using this data over here. And this is something that Berglund did back in 2006 with the Taylor resolution, used the Taylor resolution for F. And what I did is I created a general framework for how to do this type of thing, but with any choice of F, any DG algebra resolution, provided you can find a map going one way or the other, satisfying certain conditions. You can use that to say something about the deviations of the ring R. The next project that I worked on really comes from this theorem that Avramov and Piva proved back in 2002. They proved that if the bigraded deviations satisfy this vanishing property right here, for homological degree 2 and higher, that's going to happen if and only if your ring splits into two pieces, a polynomial piece and a Cazot piece. This number 2 here is significant because the ordinary deviations vanish into position 2 and higher only for regular rings. So pushing that up by 1, pushing this vanishing property up by 1, Ferraro back in 2018 conjectured that if you have this vanishing for 3 and higher instead, you'll have a similar decomposition, but rather than Q being a polynomial ring, Q will be a complete intersection. I produced a counterexample to this conjecture, and I proved that instead the decomposition looks like this. So it's kind of similar, just a little bit tweaked. I also have done some work about rigidity. So there's this really famous result that says that the deviations have this very stark dichotomy. Either they vanish almost immediately, or they go on forever. They're non-zero forever. And that's the result that I have listed up here. And this is telling you that complete intersections and non-complete intersections have this big gap in their homological behavior. Ferraro, back in 2018 in the same paper, conjectured that if you have this type of vanishing property right here eventually, then you also must have it immediately. And I have some partial work in support of this conjecture. I showed that if you have this vanishing property eventually, then you must have it in all odd positions. So it's pretty close, just kind of halfway there. Finally, I have done some work on quasi-complete intersections and Quillen's conjecture. So Quillen has this conjecture that says that if the Andre-Quillen cohomology of a map vanishes in some high degree, then the map is either a complete intersection or a quasi-complete intersection. The first of this conjecture has been proven, but the second is currently open. With Josh Pollitt's, I have some results about when the acyclic closure of a map is minimal. This is a property that is satisfied by all quasi-complete intersections, but it's satisfied by more maps than just that. When this is true, you get some structural properties of the homological algebra associated to this map. And also there's this interesting rigidity result, which previously is only known in finite flat dimension situations. So this is an interesting extension of that result to a completely new set of maps that have infinite projective dimension. With Josh Pollitt's and Ben Briggs, we are working to use some of these results combined with some other results that are out there to try and say something about part 2 of Quillen's conjecture when the homomorphism in question is large, which is an example of a morphism that also satisfies this property up here. All right, thanks for your time, and I am recording this on Halloween, so I'm going to leave off with a festive orange-colored holiday wish.